Good day everyone, I am Shaluji Betko, and for today I will be going to present the final presentation for techniques of metallurgical analysis. Today, we will dive into the core methodologies used to evaluate and characterize metallic materials. Our discussion will span from traditional wet chemistry to modern instrumental techniques, highlighting how both paradigms shape the metallurgical field today. Before looking at the specific techniques, let's define what metallurgical analysis actually is. At its core, it involves estimation of commercially important elements within ores, alloys, and finished products. By determining the exact chemical composition and purity of metallic materials, this discipline serves as an indispensable tool for industrial quality control and process optimization. We begin with Part 1, Classical Methods of Analysis. These traditional techniques form the historical bedrock of analytical chemistry and remain fundamentally important in modern metallurgical workflows. Classical methods are broadly categorized into three approaches. First, dry methods rely on the direct application of heat, such as fusion, reduction, or roasting. Second, wet methods utilize liquid solvents to drive targeted chemical reactions in solution. Finally, gravimetric methods quantify a sample by isolating a specific chemical compound and measuring its precise weight. Let's look at a practical application. The copper assay. Copper is highly soluble in dilute acids and readily forms distinct colored compounds. To analyze it classically, we can use a wet gravimetric method where copper is precipitated as a sulfide or oxide and weighed. Alternatively, a volumetric method can be used relying on precise titration with standard solutions for quantification. The standard gravimetric procedure for copper follows a straightforward sequence. First, the metal sample is dissolved in dilute sulfuric or hydrochloric acid. Next, an appropriate reagent is introduced to selectively precipitate the copper out of solution. Finally, this precipitate is carefully filtered, dried, and weighed to calculate the exact copper content. Moving on to lead, this metal readily forms insoluble compounds when exposed to specific reagents. A lead assay can be performed via dry assay, where the lead is chemically reduced, separated, and weighed directly in its metallic state. It can also be determined through wet gravimetry, where it is precipitated and isolated as lead sulfate or lead dioxide. In a wet gravimetric assay for lead, the sample is first dissolved in a dilute acid solution. Sulfuric acid is then added to selectively precipitate the lead as insoluble lead sulfate. Once the reaction is complete, the precipitate is filtered, dried, and weighed to establish the total lead percentage. When analyzing zinc, chemical properties dictate our choice of method. Zinc is highly soluble in dilute acids and forms colorless salts. Crucially, a traditional dry assay is entirely unsatisfactory for zinc because the metal is highly volatile at elevated temperatures. Therefore, we must rely on wet gravimetric methods, precipitating the zinc as a stable zinc sulfide or zinc oxide. To execute this wet gravimetric process, the zinc-bearing sample is first dissolved in dilute hydrochloric or sulfuric acid. An alkaline solution is then introduced to carefully precipitate the zinc as zinc sulfide. The final step requires filtering, drying, and weighing the precipitate to finish the quantification. Our final classical example is iron. Iron uniquely exists in two prominent oxidation states, ferrous and ferric. It can be quantified gravimetrically by precipitating it as an oxide or hydroxide. However, it is highly suited for volumetric methods involving rapid titrations with standard permanganate or dichromate solutions. The gravimetric route for iron demands an extra chemical step. After dissolving the sample in dilute acid, an oxidizing agent must be introduced to convert all iron ions into the stable ferric state. Once fully oxidized, the iron is precipitated as a iron hydroxide, which is then filtered, dried, and weighed. Now let us turn our attention to Chapter 2, Instrumentation and Methods of Analysis, which explores how modern technology has transformed metallurgical testing. Modern instrumental techniques offer significant advantages over classical wet chemistry. They deliver much faster and highly accurate results while minimizing human error. While they do require highly specialized equipment and trained operators, they uniquely enable laboratories to analyze multiple elements simultaneously from a single sample run. One core optical method is spectrophotometry. Its fundamental principle is measuring the absorption of light by colored solutions at highly specific wavelengths to determine the concentration of metal ions. The primary advantages of spectrophotometry are that it is rapid, highly sensitive, and requires only very small sample volumes. Operationally, the metal sample is dissolved and chemically treated to form a distinct colored complex. When a managed beam of light passes through the solution, the spectrophotometer measures the remaining light intensity. Because the intensity of light absorption is directly proportional to the metal's concentration, we can precisely calculate the sample's purity. Moving to structural analysis, we have X-ray diffraction or XRD. This method operates on the principle that X-rays diffract through the unique crystal lattice of solid materials. It is primarily applied to identify distinct crystalline phases and map out crystal structures. Its standout advantage is that it is entirely non-destructive and analyzes solid samples directly. Another critical X-ray method is X-ray fluorescence or XRF. Here, primary X-rays excite the sample's atoms, forcing them to emit a secondary characteristic fluorescence that identifies each element present. It is widely used to determine the bulk elemental composition of metals and alloys. XRF is fast, completely non-destructive, and demands minimal sample preparation, making it perfect for rapid sorting and handheld field testing. For ultra-high resolution work, we turn to electron probe microanalysis. In this setup, a highly focused electron beam strikes the sample, exciting it to emit localized X-rays. This allows engineers to analyze extraordinarily tiny regions of a material with exceptional spatial resolution, providing detailed elemental maps and microcompositional data across grain boundaries. To summarize the two fields, classical chemistry is often time consuming and laboratory intensive, yet it features low equipment costs and excellent absolute accuracy for high concentrations. Instrumental methods are rapid, highly automated, and multi element capable but carry steep capital costs. Ultimately, choosing a method depends entirely on your sample type, the required precision, and available laboratory resources. In conclusion, classical methods remain vital for educational baselines and standard verification work. However, automated instrumental techniques undeniably dominate modern metallurgical laboratories. In practice, a combined approach leveraging both methodologies often yields the most reliable, cross verified results in advanced metallurgical engineering. And that concludes my presentation. Thank you for your time and attention.